Howdy folks, we are going to look at optimization question 3G number 6. This is using trigonometric functions. I've just copied this out the book. Where's the book? Here. You can see I tried to trace it over to try. It still didn't come out very good, but whatevs. My excuse is the dodgy pen I have to use. But the point I want to make is that you should always have a diagram that you can work with, right? If you're doing this in your book, you should be drawing out that diagram. If you're in a test, you might need to take the diagram that's given to you, or well, firstly, if they don't give you a diagram, then draw it. But if you're given with one, you may need to start adding labels to it or something extra. Right? The diagram's useful, work with the diagram. In this question, they start with a circular piece of tin plate, but they've removed 3 segments. Okay, so that's removed, and that's removed. Right? Segment as opposed to sector. Right? The angle theta, or theta, is measured in radians. Good, I can do calculus on it. Show that the remaining area. So I've written this out because I need to, when I come up with my area calculation, I need to get it into this form. I need to show that this equation here can express area. Okay, we're going to start with area 1. This pen was too thick last time. Let's change it. I'm going to say this is area 1. Right? So what have I said? Area 1 is a sector of a circle, right? Because it's not a triangle that's curved up the top. This is a little slice of pizza, right? Or a little sector of a circle. I've got a fraction of the circle as defined by theta out of 2 pi times the area of a circle, which is pi r squared. Oh, the r is 10. Let's just write 100. 10 squared is 100, right? Pi's will cancel there and there. 100 will divide by 2. I mean, hopefully you can see this. So this is, put it all in one fraction. You've got theta times pi times 100 on 2 pi. Yeah, they cancel. That makes 50. Yeah. So you can write that step, or you can just go straight to saying that first little area is 50 times theta in radians. Now, how are we going to get the areas of the next? Of this is a weird shape. I don't have a formula for that shape, but given that this is a radius and that goes to the edge, we could just we could extend these lines out. Right? They'll be straight lines because they're going straight through the center of the circle, right? That's marked as the origin on the diagram. Right, so I'm going from the edge of the circle through the center to another edge. That has to all be a straight line, right? It's the diameter. So these are 10. Now vertically opposite angles, that has to be theta. Let's call that triangle number 2. Got to be a bit careful because that angle there is not theta, right? That angle there is, can I fit it in? I might have to draw a little arrow. The angle in there is 180 minus theta. Yeah, if there's a straight line there or there, 180 minus. This is vertically opposite. So this angle here, where I've written O for origin, that's also 180 minus theta. Let's call those, that can be area 3. And there's 2 of them because they're the same triangle. So if I said area 2 is And you might think, oh, triangles. Okay, half base times height. Hang on. Do I know the base? Oh, like I kind of do, because it's isosceles triangle. Do I know the base? No, I don't think I can work it out. No. All right, what I'm going to have to use is a different formula. Hopefully you remember it. You may not have used it since year 10. You've got any triangle, ABC, not right angled. This is not right angled. It's isosceles, but it's not right angled. I could put a line down the middle and make it right angled, but I don't think it's going to get me anywhere. If I look at that, that, and that, sine of an area equals half AB sine C. And basically that just comes from the idea that if I was to put a height in, the height would be expressed as sine of this angle here. This is angle C. Angle C, because sine gives you the opposite, the height there. So it would be sine C times the hypotenuse A. So the A and the sine C is giving you the height, B is giving you the base, and half is, you know, in the formula anyway. So that's our formula for area of triangle that we're going to use. It's the simplest way to get there. We could say half times 10 times 10 times sine theta. Right, and that gives us area 2, so that's 50 sine theta. Okay, what about area 3? Area 3. Okay. Again, very similar. So all of these lines that I've drawn in, they're all radiuses, radii. They're all 10. They're all 10 long. So I could say 2, because there's 2 triangles, times half times 10 times 10 times sine of 180 minus theta. Now, wouldn't it be nice if it kind of fitted this a bit better? At the moment there, I've got, what, 100, I've got, that's 100, then half, but then times by 2. 100 sine 180 minus theta. The book says that I should be getting an area. Let's expand it for a minute. They say the area should be 50 theta plus 50 times 3, 150 sine theta. But at the moment, I've got 50 theta. All right, that checks out. Tick. Then I've got a 50 sine theta. Well, that was looking pretty good. And then I've got 100 sine 180 minus theta. Now, if that sine 180 minus theta is just sine theta, there's my 150 sine. Like, you know, this is a clue that we could tidy this up. Right? So you can see it on a unit circle. There's a nice little angle identity. Right? Let's just choose a nice common angle. Yeah, I think that kind of looks like a pi on 6. So we've got, there's the cos coordinate, there's the sine. And I've chosen pi on 6. What happens if I do 180 degrees minus pi on 6? Well, that would be, and I've just realized, I probably shouldn't be using I shouldn't really be mixing radians and degrees, should I? We should probably be writing these 180s as pi's. Let's stick to radians. Just, my brain tends to think in degrees. Yours probably does as well. Right, so I'm writing 180 because I'm thinking about when I'm looking over here, I'm thinking about 180 degrees in a straight line. But if we're sticking to radians, that should really be pi radians, shouldn't it? Pi minus, that's better. Okay, I fixed that up. All right, if I took pi and minus pi on 6, I'd end up here. 5 pi on 6. Here's the coordinates. Oh, look, the signs are the same. Right, so that, or let's try it backwards. Let's try 5 pi. So if you had sine of 5 pi on 6, you get a half, right? What's pi minus 5 pi on 6? It's pi on 6. I'm back to here. It's a half. You might want to try it out something negative. What would that angle be to there? It would be 5 pi on 4. Right, the coordinates, we're getting all negative in this quadrant. So I've got 1 on root 2, 1 on root 2. I'm saying if you took pi radians and you minus away 5 pi on 4, all right, let's make it easier. Let's make it 4 pi. So there's my 180 degrees, or my pi. What do I get? Minus pi on 4. Where's that? It's here. What's the sign? Yep. So there's an identity here that pi minus theta, sine pi minus theta is the same as sine theta. And you may not have ever used that before. Let's see if it's on your page of notes. It should be, because I tried to give you quite an extensive page of notes. Trig note sheet is probably hidden. Periodic formulas, even, odd. I haven't looked for it. It's not up there, is it? I'm looking for a pi minus theta for sine. I've got that one. Oh, that's annoying. It's not written very clearly, is it? Or at all. Co-function formulas. That's changing functions. There's your unit circle. Inverse. Huh? Laws of cosines. No, I'm not seeing it written directly. It's a bit annoying. So for that question, I mean, there was a big clue. Unless it's there and I'm just not seeing it. Maybe you could add it on. Well, that's a shame. Seems to have pretty much everything else on here. Like it's sort of similar to the even odd formulas. Range, the period, domain. No, that's not useful. What was that? I saw something before that was similar, like the plus 2 pi n. That's really just talking about the period there, as in periodic. So no, I can't see it anywhere. That's annoying. What we've just done, by the way, only works for sine, not for cos. All right. Well, not on your page of notes. However, the question was giving you a clue, right? Once you expanded this out and you saw that there was 150 sine thetas, yeah, you could have thought, well, I've got 50 sine thetas and 100 sine pi minus thetas. Yeah, I wonder if sine pi minus theta is the same as sine pi. So we've got total area equaling 50 theta, right? That's area 1. Area 2, 50 sine theta and 100 sine pi minus theta. Yeah. Turns out that's the same as sine theta. So you hopefully were looking for it. Maybe you could just Google it, like I do go start a new set, start a new search, sine pi minus x, and it's coming up already. See where it says equals sine x? You go, oh, okay, all right, that tidies things up nicely. Now, if this was in a test or exam, they would tell that to you. Area, because there's just too many of these identities to remember, and because they're not really part of the course. We're using them from time to time, but we're not doing a subject that's focused on trigonometry. It's focusing on calculus, right? So if you needed to know that in an exam, they'd tell you. They did something very similar in last year's exam. They might give you a few. So they might say, oh, by the way, here's 2 or 3 identities that might be useful in this question, and you'd have to see that one. What I mean is they'd give you this maybe at the end of the question and say, oh, maybe you want to use this. And then they might give you another one, just so they're not making it too easy, I suppose. At this point, all we have to do is factorize out the 50, and we've got our area. It took a little while, but that's because I'm talking about it so much, working through it slowly. So now we need to differentiate. Surprise, surprise. Who would have thunk it, doing differential calculus? When you write it, right, we're looking at the rate of change of area with respect to theta, right? So write dA d theta. Do it from here. Probably easier than doing it there, although it doesn't really matter actually. Maybe it's easier there. I think I'll do it in the expanded form. Then we got 150, derivative of sine is cos. Yeah, I should have done it from a factorized form. Let's do that. So, these constants don't change your derivatives. You could just leave it. Yeah. Right. Derivative of x is 1. Derivative of 3 sine theta is 3 cos theta. Okay. So you can choose whether or not to pull constants out of your differentiation, or do it in an expanded form or do it in a factorized form. As long as that's just a constant. If that's not a constant, if there's a theta there, you have to use product rule or expand. Excuse me. So again, surprise, surprise, we're going to set this equal to 0 to try and find out a maximum or a minimum. So I'm going to say that the rate of change of area with respect to the angle equals 0. Becomes a stationary point, a max, a min, or a point of inflection, unlikely, when the derivative equals 0. So the derivative equals 0 when what? When this bit equals 0. When 1 plus 3 cos theta equals 0. Therefore, cos theta equals minus 1 on 3. Okay? How am I getting that? So I'm saying there's my little equation I'm working with. 1 plus 3 cos theta equals 0. Subtract 1 from both sides, and then divide by 3. And there's my minus 1 on 3. Now that's not a unit circle number, so we will need the calculator. All right. And it will be an angle between 90 degrees and 180. How do I know that? Because cos went negative. All right, so actually, one more little line of working. Theta equals arc cos, right? This is what I'm actually going to the calculator with. And I should write this underneath, but I've run out of room. Calculator help arc cos minus 1/3. Check I'm in radians, because in the last video I wasn't. And I've got 1.91 radians in degrees, if you're interested, divided by pi. That's about 110 degrees, just so you've got a ballpark to work with. So let's go 3 significant figures. That'll be 2 decimal places, 1.91. Okay. And the symbol for radians, just use a little C type symbol. Okay, sine diagram. Hey, that's interesting. Now, that angle there can only really be between 0 degrees and 180 degrees. I'm going to show that on my sine diagram. That's better. Okay. Doesn't make sense for the angle to be smaller than 0. It doesn't make sense for the angle to be bigger than pi radians, right? We're at 1.91 radians, a little bit over halfway. There. And I'm doing a sine diagram of the derivative, so I'm going to label that as well. Now we're trying to maximize, so let's hope it goes like this, plus minus, but we better check, right? Let's not preempt ourselves. Well, assume that's what we're doing, trying to maximize, because if we're trying to minimize, we could just put 0 in. Then we'd have minimum area. But let's do a test. Where's our derivative equation? Here. I'll just put it in a little box so you know what we're doing. I'm going to test, well, 0 would be nice. Maybe pi on 2. Pi on 2, that falls in this region. Okay, so I could have 50 times 1 plus 3 pi on 2. Now, if I make theta pi on 2, the cos is 0. So I get a positive number, right? I really only need to worry about this. Is this positive or negative? Over here, maybe we test, well, we're only going up to pi. What could we, maybe we could test 5 pi on 6, or we could test 3 pi on 4, right? We've got to make sure we're above. If you're doing it on the calculator, maybe you could do 2 radians, right? So you could, it's going to look a bit messy. You think, I'm going to test 2, I've got to be smaller than 3.14, that's what pi, you know. But 2 is a nice number for a calculator, right? So if I did 1 plus 3 cos of 2, let's just hide that for a minute. 1 plus 3 cos of 2, I should get a negative answer here, and I do. Good. Or if you want to do it with your unit circle, maybe a pi on 6, you could have seen that pi on 6 is a negative number for cos. and gone from there. So there's our maximum, right? So we would say local max at 1.91 radians approx, and I've got no idea. We're going to have to go back to the original formula and plug it in. 50, 1.91 plus 3 sine 1.91, 1.91 plus 3 sine 1.91, and then that all had to be times by 50 times 50. Can you read it? It's a bit hard to read. 236.95, 3 sig figs, 237. Okay, so the area is approx 237, and the area is in centimeters. So I could say area, or max area, approx 237 cubic centimeters. Okay, that question is done. Thank you for watching.